Yeah, shall I start?
Yep.
Nice. Cool, guys. So thanks everyone to join us. So today we're talking about what we did so far at HEMA using Kubernetes and Airflow. My name is Marcos Azevedo. I do consultant for HEMA. I was working also at Exomnia 1.5 years ago, also doing consultants. So my background experience with data started in 2019. So best 13 years of experience work with data, 7 years with the BI, and the rest with big data platforms in on-premise environment and cloud environment. So I went through a bit on this such of environment and project as well. So that's a bit about me, Daniel.
Yep. Hi, everyone. My name is Daniel, 26 years old, originally from Malta. Been living in the Netherlands for 5 years now. Started working at Zomnia 2.5 years ago as a data engineer, and now at HEMA for a bit over a year. And before that, my background was in software development when I was back in Malta.
So this is our agenda for today. We're going to talk about HEMA a bit in terms of numbers and how HEMA is located at the market, the need for cloud migration, and why we choose as a team the Kubernetes, the current solution and application architecture. I will went through that topic, and please feel free in any topic to raise the question for us. Otherwise, we can speak later about it. Later on, Daniel will go through the Airflow setup, going to each task that we implemented and how we made that, a bit with the infrastructure and a bit with the code itself, and also the other benefits for HEMA in the end of the presentation. Can you go next, please? Yes. So for Dutch people, I think that HEMA sounds like a familiar name. But for the other guys, so basically HEMA is a big retail company in Netherlands, also present in other countries in Europe, some with the franchise stores, but some with own stores. So since 1926, with 775 stores, which actually it's active. They are present in 11 countries across 3 continents. They currently have 19,000 employees. The good thing about this brand itself, they produce their goods. So basically, we own everything that we are selling right now. So we are designing that, we are listening our clients, we are collecting feedbacks on that and improve our product. So that's why we are awareness in the core market. And yeah, so HEMA produce your products in 34 different categories. Together with Jumbo, Giant, if my French is good, Walmart, Venkamp, and Franprix, we are all partners selling HEMA goods produced by us. Go next first. So basically, we are divided as a retail company in different domains. So mainly, you can see HEMA in the website, but also in some stores. And internally, we are dividing sales domain and supply chain domain with the logistic domain, product, customer, EHR. So those are the pillars of domains that we are divided now. We as a data team, for some domains, we are combined. For instance, supply chain and logistic, we are combining all in one. Same for product and customer. HR, not too much yet, but we also have finance, which is not here, which consists with all the data related to financial, the core system for HEMA. And the sales one, which is our biggest one. Since we are retail, you can imagine that most of the data goes through sales connected. Let's go to the next slide. So what was the need for the migration? What is the current picture before we start to talking about Kubernetes and other things? So first, for the data perspective, HEMA has been working with Teradata for the past 10 years, maybe more. The ways of working was kind of straightforward, of course, with many improvements and changes along of these years. So they had mainly like a lot of the domain services system that consisting to receive data, transaction the data, register new customer, control the campaign part, and also the loyalty program, and so on. So those systems basically send the data in every day via CSV files or flattened files to file system. But those files contains sometimes few rules which was requested to search system. We're going to talk a bit about this on the next slide. But then the process go through like this. So export files, flat files to file system, and through SQL scripts, they basically fetch those files available in the file system, go through different layers in Teradata, and then those data are consumed in the daily base through MicroStrategy, which is our business intelligence tool. And for other heavy users, they connect directly to Teradata to perform some SQL scripts. So that is how the flow works. If you go to the next slide, you see the disadvantage to have this environment and setup. So first, because the files contain logics in the search system. So Teradata right now doesn't receive the real raw file at all, because this was the way that was set up so far. And it's hard for the business to improve their process based on the data because they cannot see all the data available there. They always need to see if new columns that they need is not available or not in the data set, or combined data which is not available yet, and so on. So it's really like straightforward that process now. Secondly, because Teradata is really expensive, so yearly it costs quite like $1 million and something for HEMA every year, which is something that we can really reduce the cost, thinking about cloud solutions right now and the way that you can build the same platform to process the data. And the third thing that makes it more expensive, you can see the average size that Teradata have right now. It's around 60 terabytes. It's kind of hard to make the compression on that data. So Teradata does not provide the nice approach for compression, and then it makes more expensive in terms of the storage. So those three things, yeah, we need to find a way to manage that part. So if you go to the next slide, please. There are some principles and vision that HEMA looks for, like platform and this smart tech stack. So first, one center of truth. So data, business rules, triggers. So not something different that the markets look like, the other companies, I mean. Looking for decentralized this data ownership, because in the legacy platforms, you mainly see like data silos around the company. So people that like are real owner of this data and they don't like share with others. All the backend should be available, or it's available on something that we call data candleland. I'll explain a bit what it means, but thinking about one central of place that all the data that we receive goes through there, and then it's easy to just consume the data. And using that approach, which is a tool for us right now, it basically was the way that enabled the way to democratize the data for people in process. So not only Teradata as a consumer is looking for the data, but the whole company for the other applications they can also consume from there. We also have no lock, or we don't need to lock effect by any application. So we are really independent on the ways to process the data and so on. We also need to provide value for money when we buy applications. We need to empower in process and people using data, so then we become more data driven. And also we need to control with the GDPR, of course, and be more ethical in that sense, how we are managing our data, how we are really classifying our data, not expose personal data to any process or any person. Can you go next first, please? Yes. So getting the data from all domains, we are centralizing a data platform that we call it CDAP, so Cloud Data Analytics Platform. So to support that, we choose AWS. Right now, we have around 139 data sets, raw data sets that we are receiving from any source. And we have 168 consumption data products that are looking to this raw data set after the processed part. And right now we are storing around 14.1 terabyte, considering that we have many types of the resource to archiving this well, like Glacier type of the storage for cold storage, and also applying the compressing for the curated data, for instance, which is quite nice. Can you go next? So thinking about our stack that's supporting us, so those are the pictures. We have two pictures that explain how they are combined with each other from the solution perspective and application perspective. So this is our stack. Can you go next, please? Yes, so just to give a bit of overview, what is the scenario when this journey has been started? So for many reasons, people has been choose some way of working to do that. So they mainly set up some Lambda functions to go to this DCL channel to fetch the data. So the place that we store all the data available from the systems. And then through these Lambda functions, which contains different types of files like XML, IDoc, CSV, JSON, and so on, they push these also through Lambda to S3 bucket for the landing zone, for the raw zone, and later on for the created zone. To do the compute part, especially to parse raw data to created data, they implemented that using Pandas framework through Lambda function. They also used Glue for some scenarios where Pandas was not efficient due to the amount of data. And they tried to use DBT framework on top of EMR, so DBT on top of the Spark. So those three flavors was there before this platform was rebuilt. And then after that, just pushing data to Redshift and to created zone. So through also Redshift using Spectrum, they were able to fetch the data also from the MicroStrategy platform, but also using SageMaker platform for machine learning models. Can you go next, please? I think that there's some box. Yeah. So first, I would say that Lambda function wasn't enough. Consider the resource limit that this component has, and also the time limitation to run. So in the past, we haven't available for more than few minutes. I guess I don't remember the current time, but still, I think that we have 10 minutes of the time that you can use the service. And also the resource at the time wasn't 10 gigabytes. So right now I know that it's 10 gigabytes available on the service. It's really cheap service. It's really nice because it's serverless one, but doesn't handle at all the needs in terms of the data size for HEMA. So second thing is more than one type of framework for ingestion data. So Pandas through Lambda, Glue, and DBT. It's quite hard to mention that for support perspective. Thinking about Glue, for the amount of the jobs that we have, it's really expensive for the data volume versus quantity of the jobs that we have. So making the account was not, let's say, okay in terms of tool for do all the things that we need. And second thing regarding DBT is a really nice tool because it contains many features, but wasn't able to handle XML and JSON files on the large volume that we had. So just to give one example, for sales data, to process the historical data for sales data, we had around 6 terabytes of JSON files and around 4 terabytes for XML files. And at that time, DBT was not efficient or wasn't able to process that. That was the experience about the old architecture. Can you go next first? Oh, again, please. Yes. So, oh, sorry. Can you go back? Yeah. So in general, just talking about this old architecture, HEMA spent 6 months from setup, this type of the platform to production, but it was enough to support the needs in terms of the volume, amount of data sets, and scalability. So that's why this picture was rethinking to something more scalable. So why Kubernetes? For technical people, seems like cool and nice tool to work. Yeah, from the market perspective, it is. But thinking about the requirement and the things that it becomes for us, like enable us to work, first, we don't have any cloud component lock-in. So it's easy portable to another cloud. It's container-based, so you can just transfer to any cloud or on-premise environment if you want. It's scalable by default, so it's really nice. You can just add in more machines as much as you need. You have the PySpark framework supported by operator, so it's really nice. Seems PySpark or Spark as a framework can run in the container base. It's flexible to support other platform tools, so you can implement whatever other tool that you want just because you can spin up your container there. It's possible also to use in spot resource, and I would say that at HEMA we are using this resource a lot, so bringing some savings for data processing. So in AWS we are able to reach 20% of the full cost for each node that we are using this node. So instead to pay 1,000, let's say per month, we are paying only 200. And also, like the last benefits, I would say that's good to mention, it's really agnostic to support other applications just because it's container based. So right now we are using, for instance, for machine learning processing, we intend to use more API to expose our data. And also for front end perspective, we can also do application that connects to our data. About our solution architect, so how these components that I showed in this stack connects with each other. So from the left to right, we have our domain service. We have this DCL component, which basically is the place that we have all the data from the search system, which means that we don't need to connect with the search system anymore since they are sending the raw data for us through this way. DCL seems like let's say make an analogy with Kafka. It's not event streaming based, of course, but you have like many channels there that contains data about some specific data set. That's what it is. So in order to fetch this data, we have the Airflow setup. So we have here on this orange box our AWS platform with Kubernetes on top. So we designed one application which basically connects to DCL, is a REST API gateway. So then we can collect all the data that we need. It's fully parameterized. Then we will talk more about this later. But yeah, so we are able to fetch the data from there. So it basically goes like moves the data to the raw layer. So all the data from the raw perspective we have onto S3. So after that, it basically spin up a container with Spark process to move the data from raw to created. So mainly what we are doing from raw to created is adding metadata, parse the file itself. When it's JSON, we need to flatten these in different tables. Same for XML file. And sometimes we need to apply some rule just in order to have the most curated data available. So in S3 side, I think it's also nice to mention that we are using the Delta Lake capability. So it's a really nice way that you can control the keys of your data set just in order to avoid duplicates, but also you can keep in track your data, like your transaction data, at least logging that part. If you want, of course, for master data, you can do slow change dimension. So it's also possible through scripts as well. So it's a really nice feature to mention here. So a part of that, we are using Grafana and Prometheus to look into the metrics of this cluster and also show like pods which wasn't failed, for instance, or is running. We can see nodes which is running right now, for instance, and we can create some alerts on top of that. We are using NGIX to expose our endpoints, at least for Spark and Grafana and Prometheus as well. We have machine learning process that run in container base on this Kubernetes cluster. We are using Jenkins to do our CI/CD pipeline, connect to ACR and GitHub. And in order to expose our data, we are using Redshift connected to our consumption and created layer that people can connect to MicroStrategy, but also to the SQL scripts. We are not going through the rest, but just talking about HEMA data landscape. We have the business warehouse. It's really connected to our SAP system. And then we have few cubes there, which people can use through Excel, but also have few MicroStrategy reports connected there. And the third part, in the end of this picture, you can see that we also have Google Cloud Platform, which mainly store data from our online channel. So all the data that we track from Google Analytics, from Google Ads, Google CRM, they belongs to Google Cloud, and it's processed and stored on BigQuery. They are exchanging to our main data lake, which is in AWS, but also is consumed by reports and SQL queries. Any questions so far? No? Okay, let's go through the other slide. It's quite small, but maybe I can explain a bit. So, oops, yeah. So we have the domain serves as you saw on the last picture, and then we have the DCL, and then we have those two main blue box. So the first one is the way that we are segregating our DAGs, which Daniel will explain later. And then the second blue box, it's our created to consumption layer, which basically consumption products can just create your own scripts to fetch the created data, apply the rules, joins, and so on, and expose that. We are using Postgres just to manage all the metadata and parameters from this Airflow process. And also we are using parameter store just to store some sensitive password, for instance, and user on this Airflow process. We have our data lake that mainly contains three layers, so raw layer, created layer, and consumption layer. In the Redshift, we mainly divide it in two databases. So we have our data lake database, which is the mirror of our S3, and we have our data hub, which is our front end, let's say, in terms of data, that we are exposing data to MicroStrategy reports, and also for end users that are connected through SQL Server, through SQL script, sorry. And the third part that we just start is the streaming part. So if you see in the end of this picture, we are using the Node.js in container base as well to fetch our data from the Kafka, which right now is the Confluent platform, and also synchronize with S3. So we just started a project that are going to consume this data, and in future we intend to improve that, make something more streaming based, not just synchronize with S3 and expose this data. So this is our intention. Can you go next, please? Talking about the infrastructure, so how we set up this EKS cluster. So mainly we have the master, which is in AWS is managed by AWS itself. We don't have any rights on that. We are only able to create node groups. So we divided our node groups segregated by type of workload that we are running. So we have the analytics one, which is used by machine learning, by the data science team to perform machine learning stuffs. We have the Sparky one, which contains one type of machines that should be more like resource power with CPUs and memory. We also have our Airflow and the monitoring one, which contains really less resource compared with Spark, but it is really stricted to run pods related with these applications. In order to connect and make this environment more safe, this environment is set up under private subnet, which means that we don't have any component here exposed to internet. So we have a Bastion server in the middle. It's kind of the VM, small VM, that through SSH you can interact with cluster to perform your kubectl stuffs. And this Bastion server is only exposed through VPN, so it's really restricted to HEMA network than externals. So for our box security, we have our service accounts. So each service has your own service account, like Spark, Airflow, Prometheus, and Grafana. And then we have the role binding just assigned the right policies, the right roles for each service account. And of course, just back into node groups, each node group is mainly one namespace. I will share how you can restrict by namespace on Kubernetes to your pod be spin up on each node group that you set up here. Can you go next? Yes. So when you create your namespace, you have this type of script. So you inform there's a namespace. Of course, you inform the name. And in AKS, at least, the way that you can restrict your namespace to consume the node group is using this search of annotation. So scheduler.alpha Kubernetes IO node selector. So then you can set the node that you want to spin up your containers from this namespace. And then you also need to add the AKS Amazon.com /node group with the name of your node group. So whatever you set up on this namespace, it will be restricted to run on your node group. This is also a nice feature because, again, you can restrict your workload based on the needs. So when you need heavy machines, you have that. When you don't need, you can use like small machines. Can you go next, please? Yes. About the setup, so to do that, we use a Terraform. So it's really declarative way that you can create resource in cloud. It's cloud agnostic for people that is not familiar with Terraform. So this, I bring just one example how we made. So in the left side, you can see that we have a bunch of code for the cluster itself, that mainly you need to inform the name of your cluster, the version that you're going to use, your subnets that you're going to config. And one trick that I'd like to share with you guys here is regarding the tags. So not for the cluster itself, but for the nodes. So here's one example of the Spark node. Uh, the main difference from the first part is that the first part, of course, you don't need to inform the type of your machine and also the capacity type that you're going to use. But here you have to inform. So in that case, you are using only spot, and the type of machine that we are using is C5 9X large. So it's the biggest machine that is available, I mean, as VMs. You also have a block here that you can inform how you're going to scale your cluster. So your minimum size, your desired size, and your max size. So it depends of your workload, you can really increase that part. It's really flexible. And the tags itself that's really necessary to be informed is a trick on AKS at least, is the auto-scale tags. So for each node group, you have to inform the auto-scale enable equal true, and also the auto-scaler for the cluster should be owned. Uh, Not sure why, but this is something like that's necessary for AKS. So I put the link here in the presentation. If you want to see this later, there's more step-by-steps. But this is a trick for auto-scaling your node group. Second thing is regarding how you can set up your IAM role. So I just give an example here. We segregate our cluster with master role nodes and node role nodes. So then you can segregate your policy attached. So the flag goes to the same box, but you can segregate it as well according that you need. So the policy that you can have is AC2 machine setup. It's one, which kind of the S3 buckets that each node group you goes through. That's nice because then you can really segregate your cluster. The VPC resource controller is necessary for master, and ISG means the auto-scaling group policy that's necessary for node groups. So that's the way that you can maybe can guide you to set up your AKS cluster. Another tip is regarding the Spark. So mainly when you set up Kubernetes, you need to define more than one availability zone, which means that in the data center perspective, physically, you should have more than one available for the cluster, just for fault tolerance and so on. It makes sense. Can you just go to, yes. So mainly when you run your Spark workload, and if you consider to run in two availability zone, you can think in that the amount of time to process your data will increase since you're going to traffic your data in more than one data center. And also you have some kind of the overhead in the network. So I'm just mentioning here that data will be distributed across different physical network and it can take more time for your job be executed. So just a trick when you set up your node group, you can consider just one availability zone. So can you go next? Yes. So this is one example. When you set up your node group, just consider one worker, one availability zone. So then your data will not go across different availability zone. There's a penalty on that because if you are using, I don't know, I haven't seen this problem before. But let's say that the region A from AWS in, I think that in Germany or London, they goes down, your application will goes down as well. This is the penalty that you have because you're not be covered by fault tolerance, but at least you are considered to have just one data center running your workload in Spark. There's a balance, but something that you can choose. And the last trick regarding AKS is regarding CNI. It called it network interface. There's some lesson learned that I can share with you. So by default, for each node group that you set up in your cluster, a bunch of your IPs are allocated from the subnet to serve your pods. So you can imagine if you have one subnet with 255 IPs, you have this reserver to any type of workload that you are running in your subnet. Depending on the machines that you decide to use in terms of the CPU and memory, this may allocate more IPs in upfront just to have some kind of the warm up IPs when your pod needs. So it's kind of the pre-allocation of IPs. But the things like when you are running with a huge machines like this type of machine which I share with you, it can reserve in upfront like two machines can completely consume all the IPs of your subnet. Means that if you want to spin up a new node group, or if you need to do your auto-scaling, for instance, you cannot do that. And at HEMA, we had a lot of the problems with that and headache. But suddenly, together with AWS and also our partner, which is Nord Cloud, we are able to fix that. So I also put the link here, but the trick is you need to consider to reduce the amounts of IP in your warm-up network interface. Otherwise, you're going to see what happened in this picture. So this is the subnet, like private subnet in the second row. You don't have any IP available, so you cannot spin up any new node if you want. So on this fix, I put the link that you need to apply some commands just in order to reduce these warm-up IPs. Can you go next? So I would like to share just briefly how we installing our Airflow. It was through Helm. Something also how you can consider to use AFS volumes on AKS just to store the logs of Airflow, and also how you can do the ingress configuration. Do you have the link of our GitHub, Daniel, to share?
Yes, should I give you the link or?
No, you can share here.
Sorry, so let me open it.
Or I can share if you want, no worries. I have this in front of mine.
Yeah, okay.
Okay, I'll share my screen then. So for who that's familiar with Helm, it's kind of straightforward to set up some environment on your Kubernetes environment. So to set up your Helm, you mainly need to download the Helm. It's kind of the bunch of code from the repo. And then you can set up a few configurations on your Helm just to set up your service. In that case, it's Airflow. So just a few tricks that I'd like to share with you. First is regarding AFS. So AFS is kind of the storage that you can attach to your pod just to store the data. So if you need some kind of the persistent volume, that as it call it, then you can use AFS on AKS in AWS. So you need to guarantee that these
Are you sharing something or?
Yeah, are not able to see?
No.
Sorry.
Yep.
So first you need to guarantee that on the YAML values file you have configured, you have few configs from Kubernetes that needs to be considered. From AFS, at least for this storage perspective, you need to consider those two. So Airflow Kubernetes is run as a user, so 50,000, and run Kubernetes FS group, so file system group, as a 50,000. So this is the way that for Airflow, at least, you can use the persistent volume claim and connect to AFS, which is type of the storage on AWS. Second thing is regarding how you can configure your ingress configuration. So how you're going to expose the Airflow DNS. Because by default, especially because we are running Kubernetes in private subnet, we are not able to expose our endpoints. So mainly what you need to do first, you need to set up your Nginx environment. And secondly, you need to go to annotations in your YAML file and then put this slash using this annotation. So using that and also put your host that should be DNS available in your cloud, then you can expose your Airflow. And also for logging, check because I don't remember which part it is. Yeah, it's here. Let me check. Yeah, I'm not able to find it. Sorry, guys. Yeah, so this is the way that you can declare your extra volume. So consider that you have one storage claim already created in your cluster. You can just mount in your pod where your log will be stored, for instance, and the name of this. And then here you need to inform the name of your persistent volume claim using the claim name annotation. So this is our claim name, and this will be the mount point created on each pod. I think that's it for this part. Daniel, can you
Yes, I'll share my
take over?
screen.
Yes.
You see my screen? Yeah. Okay, so for the next part now, I'm gonna walk you through the setup of our code. So how do we use Airflow? How do we connect it to all different services and tooling that we have within our environment? So this is an overview, basically, of how all the tools that Airflow connects to. We see a lot of different tooling from AWS itself, so like ECR, RDS, Athena, but also to some of the third-party tools like MicroStrategy and Teams and Spark. Also, we have custom application which we use to extract data from within the DCL, which acts again as our API that we connect to get any data set into our data lake. And Airflow is in the middle. It's our orchestrator. We use it to optimize all of the processes that we have. So just to give a bit of insight on how we do it here at HEMA. So before we mentioned that we have around 139 raw data sets in our data lake. This number is growing, so it's not fixed. There are a lot of other data sets in DCL that we ingest as the need for them comes. So we wanted to come up with a way to create DAGs dynamically for each of these data sets. So rather than create one Python script per DAG, we decided to opt for a different approach in which we have one DAG, which will generate, one Python script, which will generate all our DAGs for us. The way we did that is by creating a table in RDS. So RDS is the relational database service in which we run a PostgreSQL database there. And we basically created this table in which each record or one row represents one data set that we want to ingest from DCL into our data lake. And for each of these data sets, there are 58 columns in this table, which we fill in accordingly. So just to give an example, some things could be like the job name. So the job name is something we use both for the DAG name itself, but also to launch a Spark job, which I'll get into later. The endpoint of the API in DCL, when do we want to start? When do we want to update the schedule interval? So is it every hour or every day or every Monday, depending on whatever you'd like. The way we do this, so this is a simplified snippet of the code, so to say. So we get all the jobs from RDS. So inside our dynamic DAGs Python script, we're going to call RDS. This gives us, at the moment, 139 records. And for each of those records, we extract the parameters, which are the columns. And then we create a process, which is usually ingest and load, transform, refresh our views, and given a certain flags, we can also create dynamic tasks. So tasks which you either have in some DAGs and don't have in other DAGs. Basically, what this allows us to do is that like things like start date or the schedule interval, if you want to update them, we just update them by updating the record, and you don't have to actually touch the code itself. So this is our dynamic DAG structure. So starting from requesting files, raw files from the API, going all the way down to notifying users via email. We have this process which is generated by the previous script that I showed you. We use Kubernetes pod operators, Python operators, one custom operator, and a Spark Kubernetes operator, which comes with the Kubernetes Airflow provider. So it doesn't come with Airflow, but it's something you can install from Airflow as a provider. And the reason that some of these tasks are highlighted in red is because they're optional tasks. So these are the dynamic tasks I was mentioning before. And the way that we switch on or add or remove these tasks is via flags, as I explained before in the RDS table. So you can have a flag whether we're running a historical process or if it's your daily or hourly ingestion job. Would you like to refresh the cube in our BI environment? Would you like to trigger an event in our environment or notify users? So depending on whether this is true or false, these tasks will be added or removed dynamically. So you don't, again, you just update the record without having to update the code. Just to give one example, let's say that we don't have a historical job. So basically we go from requesting raw files, checking if there was any file in the response, to then generating a specification file, a YAML file for our Spark job, create the Spark job, check the Spark job to see if it's failed or if it's complete, and then finally later on fix partitions and refresh materialized view. I will walk you through each of these steps later. But optionally, maybe you just want to run a historical process, which for us means that you don't want to ingest files into your data lake, but you just want to process the files that you already have. Like maybe you needed to update your transformation logic, and now you want to reprocess everything. So all we have to do is switch this history flag to true. And now these two tasks and these two tasks at the end are gone. So you can see that we just generate the Spark YAML file, create the job, and then check the Spark job itself. So starting from ingesting the raw files into DCL. So basically, so again, DCL holds all of our data sets. So what we want to do is that we've created a separate application. So it's not part of the Airflow code that we package and build into an image. And then we want to deploy this image so that if in the future there's another source, we're not dependent on updating the Airflow code, but we can create separate applications for it. So basically what happens in here is that there are a few variables, so like your NPI endpoint, execution date, and next execution date, which are variables available in Airflow. We use them because we query the API on a given time. So like I want data between the 8th and the 9th of February. So then this would be 8th and 9th of February if you're running on a daily schedule. We partition our data in our raw environment by year, month, day. And a file can be zipped or not. And if it's zipped, then we unzip it before we push it to S3. But this is all done in the application itself. From within Airflow, we use the Kubernetes pod operator, in which we need to define a few things. So you have your task ID and the name as well. The namespace is the Kubernetes namespace. So we run Airflow inside the scheduler, what we call the scheduler namespace, but we run Spark jobs, as we'll see later. And the Spark namespace, as Marcus explained, they also run in different node groups, which is why we've defined these different namespaces. These are arguments that you will pass to your image. So you can think of a Python script that's accepting arguments and you want to pass it through the image, and you do it this way through the arguments here. You need to define the image URL. If you need to put any secrets. The in cluster is basically telling this pod operator to read the Kubernetes configuration from within the cluster itself, rather than you providing a different file for a different configuration. Always pull the latest image. Once you're done, delete the pod because we don't need it anymore. Get logs. Also pushing through XCOM. So for those of you who don't know what XCOM is, when you have a DAG, you have different tasks, as I had previously shown you, and these tasks communicate with each other via XCOM. So XCOM allows you to pass messages or data between one task and the next. And also, if you want to, you can specify the amount of resources that you want for your pod. And I believe if you don't provide this dictionary, what happens is that you have a pod with 1 core and 1 gigabyte of memory by default. So the process goes, pull your image, since we always say to pull the image, then launch the ingestion job, which runs as an own pod within our Airflow namespace, fetch the file from DCL, and then we write to a file which we call return.json. So again, we want to be able to communicate between the tasks that we have in our DAG structure. So the first task is actually requesting the files from DCL. The next task is checking whether you have any tasks in DCL. The reason that we do that is that if there's no files available for a specific hour or day, then we don't want to start a Spark process for no reason. So then we'll stop those tasks downstream, which I'll get to later. And the way that we could pass this information from within the Kubernetes pod operator to the next task was by creating an empty directory /airflow/xcom within our ingestion code. and then each time writing this dictionary, which contains files can be true or false, to return.json. Personally, I couldn't manage to simply pass on the data by, say, returning this information from within the image. The only way I could get it to work was to write to this file and then reading it from the next task. So at that stage, we've seen, okay, we got the files from DCL or not, and now I want to check if the response was empty. So what happens is, again, our ingestion job writes to XCOM and says contains files is either true or false. And then we have a custom operator, which checks if any files are available. And the way it does this is that it takes in the Airflow context, which includes the XCOM information. And we say to pull the XCOM, the return value from the previous task ID, which we also pass a parameter. So the task ID is something that you create, you call it whatever you want to, and you just tell Airflow, like, please read the XCOM from this task. And then once we get the XCOM value, it's what we see in here. If XCOM is false, then we get the downstream tasks from Airflow, and we skip over them. So contains false, stop the DAG run. If it's true, continue the DAG run. And again, the reason that we do this is that we don't want to be starting Spark jobs for days or partitions in our raw layer that there's just no data for. This solves both errors, but also resources, so we can use things more efficiently. Now, the next part is actually launching a Spark job from within Airflow. So the way to launch a Spark job in Kubernetes is that you have to specify a specification file, which comes in the YAML template. And what we're doing basically is that we've created a file, which we include in our Airflow image. And this file we use as a template. So there are things like the name, the namespace is fixed, your job name, the image, so the Spark image that you want to pull before the operator on Kubernetes launches your Spark job. Where is your main file? So which file do you want to call your transformation? Things like time to live in seconds, which basically means if the driver completes successfully, for how long would you like it to be alive before Kubernetes just deletes it? So we set this to 300 seconds. Any dependencies you might have, Spark configurations, restart policies, driver information. So say start with 4 cores, 20 gig of memory. Each executor should start with 2 cores, 4 gig. And then also something that we've enabled is dynamic allocation, which basically allows the Spark operator from within the driver to dynamically create executors, a minimum of 2, a maximum of 100, each having the specified cores and memory that you would have here. Yeah, this means that our Spark jobs can scale up as they need to with ease. But we also figured that some data sets are small and they need less resources. Some data sets are much bigger, they need more resources. Also, you want to separate your Spark jobs. So what we've done at the moment is that we have our Spark jobs repository in which each job has a name. So for the sake of simplicity, we have job 1, 2, 3, and 4 here. Each job name here in Spark should correspond to a job name within the RDS table. The reason that we do this is that we're going to read the job name from within the RDS table, and then we're going to update the Spark template, the specification file, with that name so that we point to the right transformation file that we want to run. So each one should correspond to what we have here. And then we have our own Spark image that we have on ECR, and we basically copy in any jars that we want to use in there and our Spark jobs as well. And then push this to ECR, which is what the Spark operator is going to pull later so that we can launch our Spark job. So what happens now within this generate Spark operator, which is a Python operator, we read RDS. So again, you have your job name. Let's say that you want to set the Spark executing memory to 10 gigabytes, and we're using Delta Lakes. You want to also configure upsert keys. What we do then is get this information, load the template file, and then within our code, we basically convert the YAML file into a dictionary. We get the arguments that we got from RDS. We update this dictionary. So like here, you can see, okay, you want to update the amount of vCores, the amount of memory. This is where the job name is going to go. So it's Spark jobs job name, and it's always for us main.py. That's the script and every job that will start transformation. And then we convert it into an output in string IO. And the reason that we just return it here is because we're running a Python operator, which is running within our Airflow environment. When we just return the information, this goes straight to the XCOM. So the next task can simply read this file, this string YAML file, in which our next task is the Spark on Kubernetes operator, which actually launches the Spark job itself. I also put a link here that explains the different components of a Spark specification file on Kubernetes. So next, we create the Spark job. So what's happening here is that, again, so now we've just generated the Spark job specification file. So this is the YAML file. As we saw before, we return that output. So basically, we write this to XCOM. And what happens next is that within our DAG file, we will pull the information from the XCOM, from the task generate Spark YAML file. So this gets the YAML file, the updated one, dynamically updated YAML file from within XCOM. And then using the Spark Kubernetes operator, we launch a Spark job. Well, we communicate with the Spark on K8s operator. This is an operator we installed on Kubernetes, so different from the Airflow Spark Kubernetes operator. And we basically communicate with it. We say, okay, so within the namespace Spark, using the application file, which is the YAML file we just generated, and this Kubernetes connection, please launch a Spark job and also push the XCOM information that you get from within that Spark job to XCOM. So what the Spark Kubernetes operator does then is that it launches, it will, pull first the image from ECR that we built before. But also, we're going to launch a Spark driver. Now, once we launch the Spark driver, this is outside of the Airflow scheduler namespace, and then it basically launches its executors from 1 to n, depending on the scaling needs of it. Since now the Spark job is created outside of our Airflow environment, what would actually happen within the DAG is that this is always marked as successful, and then it just moves on to the next steps. So what we want to do is to check the Spark job. So there's an official Spark Kubernetes sensor, which basically pings your Spark job to see if it's completed or if it failed. But during the time when we set this up, this wasn't working properly, so it would just throw an exception. So what we had done and are still using at the time is that we created our own function, which uses the Kubernetes API to get the driver name and the namespace that we deployed in. And basically what we're doing is we're using the API to ping the driver pod and check whether the status is completed or if there's an error. If it's completed, we don't throw an exception. If it's not completed, so this is false, we throw an exception. In either case, we print the logs here, which are basically then picked up by EFS, and we can just see inside the diagram itself, so you can see what happened in your Spark job through Airflow itself. Next, we need to do partition management. So why do we need partition management? So basically, Spark is writing to our S3 consumption layer. And what this does is that we create partitions in this way by year, month, day. But when you add a new partition, this isn't visible to Redshift, which is the data analytics database that we use within HEMA. So what we do is that we request Athena to make a request to the AWS Glue metadata catalog, which keeps the information on the partitions and also the schema of the external tables which we create in the consumption layer. This scans S3 and finds all the new partitions that we just created. And afterwards, when you make a query through Redshift, Redshift through Spectrum will get the updated metadata so we can find the new partition, and it will give you the latest information. If we don't do this part, you could be writing data, you query it, but it never shows up to the end users. So this is why we need to do partition management. It's quite simple. We use Boto3 basically to connect to Athena. We get the external schema, external table name from within the RDS table, and we call here this query MSCK repair table on the schema and table, and this fixes the partition for us automatically. And the next then part is refreshing our materialized views. The materialized views, why do we need them? So let's take, for example, we have our BI analysts, and our BI analysts want to query the data that we have in S3 in our consumption layer. So what they could do is that they could directly query the external tables, which I just shown before. So through Athena, or Redshift, query the external tables. What this would mean is that if you query the external tables each time, you have to read the data from S3 every time, which is slow and it's more costly. So what you can do instead is create a materialized view, which is basically a pre-computed view of the data that you have in the external table. And this way, when you query the data, you don't have to actually go to S3 every time. It's stored within the materialized view, but it also means we don't have to maintain tables within our data warehouse. This is faster and it's more effective. And also, if you really want to, you can add your own logic within this view, which again isn't being computed each time you query it, but it's computed only once. But we're not doing that. We're trying to move all our logic into PySpark, so we're not coupled with Redshift. And again, this is how we refresh the views. So we just connect to Redshift. We'll get the schema name, materialized view name from within the RDS table. We run this command, so refresh materialized view on the schema and view, run that query, and the view is automatically refreshed for us. And just the last parts. So sometimes we need to also refresh a BI cube once we refresh the view. So our BI tool at the moment is MicroStrategy. What we do is that we get the list of cube IDs, we connect to MicroStrategy via its API, and we just make an API call. So we automate the refreshing of the cube. The reason that we do this is that maybe a cube was set to refresh every day at 8 a.m. because the file is expected at 6, but today the file came in at 9 a.m., so you refresh the cube for no reason. This way, we avoid these scenarios because we refresh the cube as soon as the data has been processed. And sometimes we also want to trigger events within MicroStrategy. An example of an event is, say that you have a report and you want to extract an Excel sheet of it and then send it to a few users via email. You can set up the extraction and email through MicroStrategy, and then what we do from our end is just call the API so that we trigger these events. And finally, sometimes we want to inform users via email that, hey, you've gotten the data set has been processed. Now you can go and start querying. So what we did again in RDS, we put in a few columns like to who we want to send it to, people in CC. Of course, this flag should be true. In that case, we've set up an email template, which we load and update via Jinja, which is how we do it this way. And we use a simple email service, so SCS hook that's available within Airflow so that we can send an email to these users with this HTML content. And finally, as a way to alert ourselves within our environment that something went wrong, because again, right now we have maybe 150 DAGs running, and this is growing, and it's a bit difficult to just maintain by just looking at it. What we've done is that using Teams, whenever a job fails, so a DAG run fails, on failure, we get some information about the DAG from the context of Airflow. We also get the data engineer in charge of that data product, and we send an alert within Microsoft Teams to alert the data engineer that, hey, something went wrong and you should probably go check this data set to see what's happening. And yeah, finally, again, sorry, the impact for HEMA from this was that we set up most of the things in Kubernetes. We are, again, trying to move our transformations toward Spark so that we are on Spark. ingesting data from the DCL is a separate application. The reason we've done all of this is that we don't want to be stuck in one cloud platform. If today we're in AWS, tomorrow want to move to Azure or GCP, for whatever reason, we can easily just lift and shift towards that platform. The way that we've set up Airflow with dynamic DAGs means that we can really scale up the amount of DAGs that we have for the data sets to ingest them, transform them, and have them readily available within our data warehouse. Also on EKS and through Airflow, we've enabled data scientists to run their machine learning models, train them on top of CDAP. Since this project started, we've also increased the Net Promoter Score, which means basically that customers are happier with the experience that HEMA is able to offer them. And again, the dynamic DAG generation means that we can really get data products from source into our data warehouse really quickly, allowing us to focus on creating other data products and with business logic, and then the business HEMA can focus more on their customer experience. So, yep, that's it.